Cool. Yeah, welcome. Welcome to this session about rethinking reactive architectures. Happy to be here on the last day of this conference. Happy to be here, even if it's in a hybrid mode. Again, in front of real people, not in front of a Zoom call. That's fantastic. And yeah, greetings also, of course, to the people who join online. Rethinking reactive architectures, first things first. Who am I? I'm David Leitner. I'm working as a coding architect in Vienna for an Austrian company called Square Solutions. So we do a lot of work together with big financial institutes, big insurance companies, also a lot of startups and scale-ups, fintechs, proptechs, medtechs, all this kind of stuff. And we do there a lot what I will talk about today. And that's, I think, the advantage for you. I don't want to sell you a product. I don't want to sell you a training. I'm just here to talk a little bit about reactive architectures because the guys from NDC asked me if I want to talk about it. And I said, yeah, Oslo is a great city. Let's come here. Let's give you a little bit of insight what we experienced with reactive architecture so that you maybe don't make the same mistakes as we did. I'm a traditional guy, so if you have any questions, feel free to send me an email. I'm also on Twitter. I'm not really there. I just have an account there, but usually I check my PM, so if anything is unclear afterwards, please feel free to reach out there. And if you want to see the mountains I'm going up and down, you can also follow me on Instagram. There is basically my personal life happening. But let's come to the stuff that really matters. And the stuff that really matters is obviously reactivity, right? And we see reactivity as a huge buzzword these days, right? We see it in many different aspects of our industry. We have frameworks like React, right, which obviously tend to be reactive, right? We have Spring Reactor, which is kind of a reactive implementation in the Java or Spring ecosystem. We have reactive extension, which originated actually from the .NET community and which are broadly available in nearly all languages. So there's much more on this reactivity, on reactive programming. And so the question is what it is all about. And the definition of reactivity is very important for this talk if we talk about reactive architecture. But on the other hand, it's also very simple. It's basically about programming and designing upon asynchronous data streams. That's what it's about, right? So we speak about streams, right? Finally, everybody loves to speak about streams, and this is the new favorite topic of everyone. We need to stream. We need to have streams within our architectures. And I still have the feeling in many situations people are overwhelmed by this term, right? Because architects start to talk about streams, and sometimes people don't fully understand. And I think it's important to kind of deillusion this magic behind streams, because a stream is not a very high sophisticated concept. It's just a data container, basically. And if you think about data containers in modern programming languages, then we usually have them on two axes, right? We have them on the axis of time, and we have them on the axis of space. Okay? Sounds high sophisticated, isn't it? Yeah? Give me a second, and you will understand why this explains streams very well. So in singular time, or in singular space, and in synchronous time, we have something which we tend to call a value, right? And a value has a getter and a setter. Okay, that's clear. Every programming language, every modern programming language these days has a concept for storing a value. If we go now to plural space, right, we have something which we tend to call a collection. And the collection tends to have an iterator and kind of a generator. And now it's getting a little bit more interesting, because if we move from synchronous time to asynchronous time, we tend to have something which we tend to call promise, right? And many modern programming languages these days come with out-of-the-box support for promises, right? And those promises then usually have a deferred and usually have a resolver. Another question, of course, is what is on the left top side, right? Well, it's obvious. That's where the stream lives, right? And the stream is basically, you can think of it like a collection of promises, right? It's something in plural space and asynchronous time. And the stream then basically has a subscriber and an emitter. And that's a stream, right? It's just another data structure. The point is just that many languages, many frameworks didn't treat streams as first-class citizens. So there's not a native implementation for this data structure in many programming languages. But in a nutshell, it's clear that it must exist if you take a look at this matrix. And that's, for example, where reactive extensions jump in, right? Which I mentioned earlier, which is basically providing stream implementation and for different programming languages. Okay, so this was a short intro to streams, so that I can be sure that everybody knows about streams. what has this to do with reactivity? Well, as I mentioned before, reactive programming is programming with or designing upon asynchronous data streams. And I always bring a very simple example to make this point clear, what reactivity really means. And I usually show this with code because most of us, I guess, are still engineers or had a background in engineering. So most of us would understand this very simply, I hope. And if we take a look at a very simple code snippet like this one, then we have a variable which is called counter, and we have a variable which is called doubled. And doubled is basically counter multiplied by 2. So it's 4, right? That's not hard to compile and to run in our heads. And this test, of course, would succeed. But what happens now if we change the value of counter, right? If we update it, if we set counter to 3? Well, we assume that doubled is counter multiplied by 2. So we could think that doubled should be 6. Of course it isn't. We all know that it isn't, right? Because if we want to have doubled to be 6, we need to reassign it, and we need to recalculate it, and we again need to reassign doubled to counter multiplied by 2. And then it will work, right? And that's basically the main criticism of the reactive community on the way how we develop or how we design things, right? Because this relationship between counter and double is very implicit here. This is an idea that just exists in our heads. We need to take care of this. We need to know about this. But it shouldn't be like this. It should be very explicit, right? It should be part of the language, and it should exist over all time, actually, right? So we want to basically bind counter and doubled. And one guy who realized this very well in a blog post is Paul Stovall. He wrote a great article on a very similar subject about reactive programming, and he introduced something which he tends to call the destiny operator. And the destiny operator is a thing to bind, in our case, counter and doubled. And how does this look like? Well, it's just a simple concept. We say, okay, we introduce here now the destiny operator, and that's him, right? It's just a little bit a different assignment. And when we say we make a destiny operator, basically whenever we change counter, this will also update our doubled value, right? And with this destiny operator, we basically project the counter value into our doubled value. And this would then probably work. Of course, it's a theoretical concept. And in reality, if you want to achieve this, this is always working with streams. So we always get kind of this binding by utilizing streams. And in a pseudocode, this would look like this. We have a stream with an initial value of 2, right? So our counter stream has a value of 2. When we have another stream, then we basically take the value of counter and map it and multiply it by 2, right? So we have a second stream, which is then called doubled, and this has a value of 4. So, and that's important now. We project the data from our counter stream into our doubled stream. That's what we basically do, and we'll come back to this later. And then we can update our stream, of course, and we do this by emitting a new value. So we go to counter, emit value 3, right? This leads to the fact that counter has a new value, has an additional value in its stream, and this will automatically, of course, also update our doubled stream. And then we can say, doubled value is 6, right? And that's reactive programming in a nutshell. And this was all pseudocode, but in reality, it would look very similar, right? If you, for example, take reactive extensions, and if you would implement the same thing with reactive extensions, we would say, okay, we have a behavior subject. Behavior subject is basically just a stream with an initial value of 2, right? And then we can say, we derive from this stream another stream, and we take the counter stream, map it, multiply it by 2, and whenever we change the counter, we just emit a new value, and doubled value would then be 6. This test would work, so it would really be green. And more modern frameworks, like for example Svelte, which is popular these days in the web development, they even took this concept of the destiny operator further, and they really implemented kind of a destiny operator. What they do is they say, we have a variable counter, which is 2, and we have a variable doubled, which is counter multiplied by 2. And you see this tiny little prefix here, this $sign. And this $sign basically tells us that this is reactive value. This will change whenever something that affects this value changes. So when we then assign 3 to counter, the assertion that doubled is 6 will still be true. And again, this will work, and basically that's reactive programming. That's what you need to understand about this, right? And now we basically come to the topic of this talk, because these concepts, and that's why I'm so eager on people to understand these concepts of reactive programming can also be applied on reactive architectures or architectures in general as well. Okay, let's get this started. So, as I mentioned, I work a lot in financial institutes, and we, of course, do a lot of distributed systems and stuff like this. So I took an example use case from project which kind of looked similar, which I worked for a while ago. And let's assume we have a few services, right? We have a user service, and then we have an account service. So basically, the user is the client, the customer of a bank, and the user can have multiple accounts. And these accounts then basically can trigger transactions, and transactions are usually stored in something which tend to call ledger, right? So very, very simple example. And then we have a web banking application, okay? And from this web banking application, we can trigger a new payment. And I can say, I want to transfer 20 euros from my account to Lisa's account. And if I click on perform the payment, it will go to the user account and will say, hey, transfer some money from one user to another. This will basically trigger a payment against the account service. And then actually this will trigger a transaction on the ledger. And if all this works fine, we get back all the responses, everything good, everything great, the payment was successfully executed. It never works like this, unfortunately, right? That's the happy, happy, happy part, right? In most situations, we have a different scenario. We trigger a new payment, we create this payment, and basically we create transactions, and then we have ledger. And most people who ever work with a ledger know that ledgers are, they kind of special systems, right? And at some point in time, they're maybe kind of lazy, they have high latency, they don't want to answer you, whatever, right? And this ultimately leads to this loading, right? To this kind of loading stuff all the time. And if you've ever been sitting in front of your PC and did a payment, and you were waiting for this payment to be executed, and you're stuck with a loading screen, this makes you really nervous, right? This is just a bad user experience. And this can take some time, so let me quickly drink something in the meantime. And once the ledger is maybe back, it could be back. In the best case, in the worst case, it runs in a timeout or whatever. Once the ledger could be back, we of course get back kind of this information, and the payment was executed successfully. And even if this works, it's still very bad, right? But in many situations, it doesn't really work, and that's why we try to start to solve this problem with retries. We know all these things, right? With retries, with timeouts, with kind of circuit breakers, and that's kind of sophisticated because we need to start to synchronize all this stuff, right? Because if the ledger engineer says, okay, our timeout is after 1 minute, right? And if the account engineer says, we retry every 5 seconds if lazy ledger doesn't answer, right? Then we run into this problem that you basically DDoS your own system, right? And this, you don't want to be waked up in the middle of the night by a call which tells you, hey, our system is DDoSed, and then you basically find out that it's your own services because you didn't synchronize retries and timers and all this stuff. So very complicated. It never really worked for us. It's just a pain in the ass, to be honest. And that's kind of the first generation of microservices, I would say, this heavily synchronously integrated microservices. And we found out that it doesn't work, right? And that's why we started to take a look at this example and realized we need to integrate this differently, right? And this is when we basically didn't talk directly from the account to the ledger, but introduced a queue in between. So we said, okay, here's the queue now, and whenever a payment is triggered, we take this payment and basically forward it to the queue. And when it's stored in the queue, we're basically done, because the queue guarantees us that at some point in time when the ledger is ready, it will start to process it. And I think that's common sense these days, but it's important to understand that here the wording now changed, right? We didn't execute the payment, we accepted the payment. So in terms of HTTP codes, we switched from 201 to 202, right? So we told the customer, okay, we accepted your payment, we will work on it, but come back later and check if it's already done. And once the ledger is then available, he will pick up the message and we will execute the payment, of course. And this, of course, already helps. This makes the system more resilient and helps us in decoupling from high latency services. And you know, the rule of bottlenecks is if you isolate one bottleneck, you will spot the next one, right? So maybe we spot, okay, there's an issue between user and account communication. And if you spot this bottleneck and solve it, you find another bottleneck, right? And ultimately, this led us then to this effect that we kind of built heavily asynchronously integrated services. And this were the big times of tools like RabbitMQ and ActiveMQ and all this stuff, right? And that's kind of the second generation of asynchronously integrated microservices. And as I mentioned, it solves quite a couple of problems which we had before in only synchronously integrated services. But there's a big elephant in this room here, right? There's a big problem, there's a big downside of this general design. And you will realize this problem when you talk to your product owner, when you talk to your PO, right? Because your PO will tell you, you know what? It's important that as a customer, I want a transaction to be booked by the ledger. This is what no PO will ever tell you, right? As a customer, you don't care where a transaction is booked, right? You don't care if it's booked in the ledger or if it's booked somewhere else, right? And your PO will also not say, you know, as a customer, I want my account service to update my balance. You don't care where this is happening as a customer. You just want to have a correct balance at the end of the day. What a PO would probably tell you is that as a customer, I want to transfer money to someone else. And then you say, okay, that makes sense. That's kind of a, yeah, we could probably do this as a bank, yeah. It could make sense to implement this feature. And then you start to realize, okay, I will try to understand how we do this in our implementation. And then you need to go to the user team, to the user service team and say, hey, you know, we have this new crazy requirements to trigger a payment. Can you please extend your API endpoints? Can you take this payment and then forward it to the account service, to the guys from the account service? And I will talk to them and I will tell them, hey, please, can you extend your API? We need the availability to create kind of payments, and the user service will trigger you, and you need to then take this request and forward it to the ledger, and at some point in time the ledger will maybe send you back a transaction, talk to the ledger and define the Swagger APIs and all this stuff, and then you need to go to the ledger team and say, hey, you know, there's this new user story where we need to implement this transaction on the ledger side. Can you do this? And you know, you get called by the account and the account got called by the user, and you just say, poof. Okay, this doesn't really work. This doesn't make us fast. This doesn't really make us agile. And this doesn't allow us to deliver fast user value or customer value. And that's what we tend to see very often still these days, this entity service anti-pattern, right? And that's a big problem in microservice architectures, that people take, you know, the entities from the database and say, okay, we have a user, we have a bank account, we have transactions, so build those services around it. But that's not what we really want to do, right? What we want to do is we want to create services along customer journeys, right? And I had the pleasure to talk on Wednesday to an old friend of mine, I would say. I met him at a couple of conferences already. Trot, he had a great talk, I think, here also yesterday. And he showed me a very interesting paper. And this paper is interesting because it's from 1972. And it talks about the criteria how we should modularize systems, right? Or decompose systems. And it's from 1972, from Panas. And he already stated in this paper from 1972 that we shouldn't structure our applications based on process steps, but we should structure them based on end-to-end flows, right? So it took us half a decade to re-understand this in microservice architectures again, but yeah, finally we are there. So yeah, better late than never, but that's the idea, right? So we want to create services along customer journeys. And when you get this requirement as engineers, you know, engineers are clever guys, right? That's why they're engineers. And what we do then is we say, okay, yeah, we do now customer journeys, but we still, you know, we need this entity data. So we basically often just rename this to domain services. And in front of those domain services, we build our beautiful customer journeys, right? So there is no problem in software engineering which you cannot solve an additional layer, and that's also true here. So this payment service then usually would call the user service, would call the account service, would trigger transaction, the ledger service, and the web banking application ultimately would call this one. And then you have a team which is taking care of this customer journey service. And we see all these dependencies, right? We have kind of this upstream dependency that leads to the ripple effect. So whenever, for example, the accounting service is down, right, it will directly impact our payment service. Or when the ledger service is down, it will directly impact our payment service. Or if the user service is down, it will directly impact our payment service. So it's not fun to work in the payment service team, right? And if we go back to our PO and say, yeah, no, we reshuffle our architecture, we now work with customer journeys. Can you tell me again what you needed? Okay, it was about this payments, this transfer of money. Well, let me think. Okay, I need to go to payments team, I need to go to user account. Okay, didn't really improve the situation, right? I need to go to 4 teams now instead of 3. And even worse, many projects I've been in started to utilize the backend for frontend pattern, which is a very great pattern for specific use cases, to implement the customer journeys, right? So we have the customer journey of payment and in the web backend for frontend, right? And then we have more backend for frontends, for example, a mobile backend for frontend for mobile clients, right? And we then implement there the payment flow as well. And this leads to a lot of duplication, right, of this payment logic. And that's actually what we don't want to have to duplicate business logic. And then ultimately this is owned, I guess, by a different team, usually the team that also owns the mobile applications. And then basically all even gets worse, right? You need to go to 5 teams now and you get the point, right? So especially, that's why I brought this on the slides, because I see this often, this misusage of doing this kind of customer journeys in our backend for frontends. That's not the idea of backend for frontends. That's not what Sam Newman defines in this pattern, right? So backend for frontends are not about domain logic, right? They are just about aggregating together data and bringing it in a shape how we expect it on the mobile client, mainly to avoid overfetching and mainly to avoid over-requesting, but not about defining customer journeys there. Okay, but yeah, let's get back to the problem of customer journeys, right? So this was the issue. Well, and if we have now multiple customer journeys, let's say we have another customer journey which shows us our current balance and shows us our latest transactions, then this customer journey obviously also has dependencies to a ledger to get the latest transaction, and maybe also has a dependency to account. And this then on the long term leads to a lot of resilience issues, right? Because if account is down, and if we cannot access the account data, this will have a direct impact on our balance and our payments customer journey. And there's a big underlying problem behind this. We are kind of all aware a little bit of this, I have the feeling. And if I talk to people, they fully understand this. But the underlying problem is what I tend to call this mismatch of customer journeys and entity data, right? So there seems to be kind of a mismatch. And if we think about entity data, each system has entity data. We cannot really avoid to have this, right? So we have, for example, users, we have accounts, we have transactions. And on the other hand, we have these customer journeys, right? We have payment, we have an onboarding, we have fraud detection, stuff like this. And the interesting part is now this relationship between customer journeys and entities, because it turns out, for example, that payments would need a user, would need an account, would need a transaction, right? And onboarding would again need a user and would again need accounts. And fraud detection probably only needs accounts and transactions. And we see this is not a one-to-one relationship or one-to-end relationship. This is an end-to-end relationship. And this turns out to make things very hard. Because if we then design our system like we did before, then we end up ultimately always in this kind of distributed monolith, which makes everything really hard and yeah, it doesn't really bring that much value. So how could we solve this issue? Well, we could easily say, yeah, let's get rid of the entity services or the domain services. Let's move the entities into the customer journeys, right? So on a theoretical level, it could look like this. The onboarding service now has user and accounts. The payment service has user accounts and payments and so on and so forth. But you know, this would, first of all, make our services very autonomous, very independently. So if payment service doesn't work, this has no direct impact on fraud detection or on onboarding. That's fine. So we have high service autonomy. But I mean, as you already see, we have a lot of data duplication here, right? So we have account on 3 different services spread, and you will have a lot of data synchronization problems. And that's important now, because when I talk to people and when we talk about distributed systems, I often have the feeling that that's not clear, but it should be very clear. We should very explicitly define who owns data in our distributed systems, right? This is very often just an implicit definition somebody makes at some point in time, but it should be very explicitly defined who owns which data along our distributed system. And we could easily define this here. We could say, you know, onboarding owns the user. Payment owns the account and transactions, right? And when we, for example, need a user in payments, then we go to onboarding and fetch the user data from there. But then again, we have the synchronous calls, right? We didn't want to have them because if onboarding is down, we have a problem in executing payments. And then people start to introduce caching and all this stuff, and you have two big problems in software engineering, naming and cache invalidation and off-by-one errors. And it just doesn't really work. It doesn't really make sense. It makes it a very complex thing which should be much more simple. And so there must be a better solution to get around this mismatch of customer journeys and entity data. And it turns out that there is one, right? It turns out, if we think back what I said in the very beginning when we took a look at the simple code snippets, then I said one sentence: we projected data from our customer stream into our doubled stream. And this concept of projecting data from one place to another place could also help us in this direction. So if we think of our onboarding service who owns the user and our payment service who needs a user, then we could think of it that in the payment service we want a projection of the onboarding user. So we would like to project from onboarding to payment, right? Our kind of users. And if we think this in DDD terms, then we would say we have on the one hand side a user aggregate, and from this user aggregate we project into our user read model. And then we have, whenever the user aggregate changes, we have a user event, and this actually triggers the user read model to be updated. And when we want to update the user, we have a user command, and the payment service would probably trigger this user command to update the user aggregate, would then again create an event. This event would update the read model, and that's basically CQS in a nutshell. And we get this done by utilizing streams, right? Because this event goes into a stream. And again, as we did in the very simple code snippet, we could even use stream transformations. We could say we transform the user from onboarding, because the user in onboarding has 50 fields, right? But we in payments just need 5 of them. So we kind of map it and get rid of 45, shuffle these 5 in a way, format them in a way that we can simply read them for the payment use cases. And that's basically where we switch to technologies like Apache Kafka or Apache Pulsar, right? And in our use case, that can be achieved again very simple. We can say, if a user gets updated, we trigger an event, we store this event that the user got updated into our stream, right? So we move it there, from there on we forward it to the payment service, and in the payment service we then basically store it in our user read model. And if the user changes again, we can basically do the same thing, and the event would again update the user, right? And we can do this basically for nearly all data we have in here, like transactions, which we can push to the stream. And whoever needs a read projection of these transactions can directly read it from the stream. But it's important to understand that, this is just read data. This is data which we don't want to manipulate anymore. If we want to change users, we will always go via commands or via requests to our onboarding service. And then people usually ask, isn't this event sourcing? Well, it could be, yeah? Let's go a little bit into detail to understand this question, because it's a very good question. Well, if we do this, what I just showed you, that we kind of get events, and this event should update, for example, the state in our onboarding service. In addition, it should also trigger an event to our event stream. Then we usually have this problem that if one of those two doesn't work, we cannot really revert the other one, right? So, for example, if we send an event to our stream, and the stream said, okay, cool, I got it. And then we try to save the state change to our database, and our database, for whatever reason, doesn't allow it, then we can't really get back the event which you already published to the stream. And you can turn it around however you want. You get into this problem. And this problem is caused by the issue that we, of course, don't have transactions over streams and databases, right? So we don't have this concept of being transactional here. So we can never ensure that data for sure lands in both persistences, so to say. And the solution to this problem is basically something people do very often. So we go, when we get a user update, we take it, we store it in our database, and our database then updates the user table, but also updates in the same transaction the user events table. And this is what we tend to call then usually the outbox table. So we trigger and record into this user events table, and we can ensure that both these records are stored in the database, right? So we can ensure this because we have a transaction over this kind of two updates or to create statements in our database. And then we basically just go to the user events and we kind of stream them into our stream. And this is usually done by change data capture, or you implement a watchdog, or you implement manually a process which checks your user events table all the time and understands basically if there's something changed, and we publish it to the stream, right? And that's what we tend to call the outbox pattern. And this is a pattern to solve this issue which I showed you before. But from my opinion, it's heavily overused. I wrote a blog post on this if you're more interested in this, why we shouldn't overuse the outbox pattern too much, because there are much more simple ways to achieve this. And another way to achieve this is if we get a user update event, we basically just forward it to the stream. And then we say, okay, we're done. We have it in the stream. And then on the other side, we listen to our own event and we say, okay, user updated event. That's also interesting for me, right? I take basically the user and update it in there. And that's what we tend to call the listen to ourself or listen to yourself pattern, right? We really listen to our own events and there kind of get rid of this transactional boundary and don't need to implement an outbox and all this stuff. And another option, and now we get to event sourcing, is basically event sourcing to solve this problem, right? And event sourcing, for those who don't know, is basically that we sum up all the events within the system, and those events of the system are kind of the current state of our application. That's kind of the idea. And I always explain this with transactions because it's very simple. If you have a couple of transactions, so you have a transaction which gives you 20 euros, and you have a transaction which gives you another 10 euros, and you have a transaction where you have to pay 5 euros, and you have another transaction where you get 7 euros, then based on these events, you could always kind of understand your current balance. So after the first transaction, your balance is plus 20 euros, right? After the second transaction, your balance is plus 30 euros. After your third transaction, your balance is 25 euros. And then basically the balance is 32 euros. So the important stuff here is that we move the source of truth to the left-hand side. So the source of truth are our events, and based on these events, we can always derive our current state. So we wouldn't store the balance in the table, and we wouldn't update the balance there. We would just store the events, and based on these events, we can always calculate the balance. And event sourcing is, of course, a very interesting topic, and we could have a separate talk on the downsides and the challenges, but also on the big advantages. But basically, the idea is simple as that, right? And if a new transaction happens, yeah, again, we can update the balance, and we can say it's now 35. And implemented, it's of course with streams in most scenarios. So we can easily say that an onboarding service now gets this user updated event. We just store it in a stream, and basically whoever is interested in those events, in those user information, can build up its read model based on those events, right? And we can have here an onboarding a user, and we know its age is 21. And when we are interested in the age of users, also in the advertisement service, we can basically also consume it there and store it in our read model. And then, of course, we can trigger new events. We can say, okay, the user is now 22, right? And then basically we can update the user age on both services, and we will have then the user age 22 everywhere, right? And somebody else could trigger a change. So somebody from the outside could say, okay, the user should now be 23, and so on and so forth. And that's what I tend to call global event sourcing, and I'm not a big fan of global event sourcing because from my perspective, it breaks the boundaries of information hiding and lots of data isolation. So what I usually try to recommend is when we do event sourcing, we do something which we tend to call local event sourcing. So very similar concept, but our onboarding service gets a command to update the user, right? We kind of store this command as an event in our stream. So the user got updated, is now 21. And we basically forward this event then to our global stream, to our published stream, which everybody can read from. And basically we have this event in here. And even if this is the same Kafka cluster in the end, right, doesn't really matter, but I think it's very important that we say this event store is owned by a particular service. Otherwise you end up in, this kind of database integration, which we had a decade ago and which we didn't really like. And now you would say, okay, basically it's the same. You just have two streams now, right? You make things more complex. But I think we gain a lot of benefits here, right? Because first of all, we can ensure some kind of business rules on onboarding. We can say, a user isn't allowed to have a negative age. A user isn't allowed to be older than 200 years and so on and so forth, right? And we have this information hiding. And we hide also the implementation details. So if at some point in time we say, event sourcing is a great idea, but doesn't make sense in this particular use case, so just replace it with a PostgreSDB and change data capture our changes from Postgres to the stream, then we can easily do this. And last but not least, you see we didn't update or we didn't publish the same event from our local event store to the global event stream because we can customize it. We can say, I don't want to actually expose the data, how I store it internally, because maybe it's not easy to read, maybe it's not easy to understand. We publish another event. We publish a user age changed event, which is easy to consume, which is easy to interpret by users. And that's basically the idea. And event sourcing, both kinds of event sourcing solve this problem, which we can solve with the outbooks pattern or the listen to yourself pattern. So too long don't read. Event sourcing can be used, but is not mandatory. Yeah, that's what I want to say here, because I often have the feeling that if people start to think kind of a little bit reactive, they always think it must be event sourcing. It doesn't have to be. And if you go with event sourcing, my advice, prefer local over global event sourcing. And well, if we now go back to this initial problem, right, then we see that this idea of this reactivity, which we introduced in our system architecture, already solved a couple of issues, because when we now have the onboarding service being down and we cannot kind of access user data, we don't need to do this during executing payments, because we have kind of projected all the user data we need for payments into our payment service. So that's an important concept. We co-locate the business logic with the data, right? So we try to make everything available at runtime. So we don't want to pull for users during runtime when new payment should be executed, but we want to get the users pushed into our services, right? Because this makes our system more resilient. And I show you a use case to make this a little bit more understandable, maybe. So around 5 years ago, I worked for a big Austrian bank, and we recreated the mobile banking there. And well, it makes, of course, a lot of sense to first understand what do we actually need. And we did some research, and it turned out that if you build mobile banking, right, 93% of the users, what they basically do with this app most of the time is checking the current balance and checking the latest transactions. Maybe you see yourself, if you take out your phone and check mobile banking, that's basically what you do, right? So that's 93% of all the time users spend on your application is basically they will do these two simple things, checking your current balance and checking your latest transactions. And then they initiate some new payments and add any other functionality, like locking your card, all this stuff. It takes you months to implement, and then basically is used nearly never. So also from an HR perspective or from a prioritization perspective, a very important or interesting numbers. But in the context of software architecture, we can use these numbers very well, and we can really build our application in a way that it supports those numbers. So we could basically say, if a user triggers a payment, yeah, simple as that. It goes to a transaction, the transaction is stored in a stream and is stored in a database, and from there on, we move this transaction over the stream, the overview service consumes this transaction and stores it in a read model. And this read model can also be persisted, of course. So maybe we store the transactions here on the overview service as a persistent read model, and then when a web application, a mobile or web banking wants to read our current transactions and balances, then we basically just go to this one persistence here. We never go back to the payment service to read current balances and latest transactions. We always only just go to this tiny read model which is persisted here. And this brings a lot of advantages when it comes to resilience, because you can start to burn your onboarding service. You can even start to burn your payment service. You can basically start to burn nearly your whole architecture, right? But as long as the overview service is available, you will be able to serve 93% of what the customer needs from you. And this is reading latest transactions, reading current balances. Yeah, maybe this data gets stale after some seconds, right? But you can still deliver the customer an experience that he can check his current balance and your application isn't down or doesn't send back a 500, right? And there are multiple more advantages if you think in this kind of reversing from pull to push, if you think in this kind of reactive patterns in architecture. And another advantage is that we can easily horizontally scale, right? We can spin up a second overview service. And this overview service, when it spins up, it basically builds up again this read model. So we build up a read model, and we have an independent instance of the overview service. And we can then, from our web banking application, read from both services. And if one of them fails, then we can easily deal with this problem because we can easily horizontally scale. And that's a big advantage, of course. And there are even more advantages, right? In terms of resilience, we have, this kind of autonomous services and this horizontal scaling, but also in terms of user experience. If we take the concept of a payment, right? Then, for example, in the web banking of Lisa, she triggers a payment to transfer 20 euros to me. This goes over our kind of HTTP request to the payment service. We store the transaction in the stream. This transaction gets forwarded to the overview service. We store it there in the read model. And basically, we can directly push it forward down to the UI, right? And now you say, how should this work, right? Because we push it down and the UI basically takes care of this and shows the transaction without any F5 or something like this or any reload. It's really pushed from end to end. And now you say, well, that's not really working because we have REST here and REST is pull-based, right? And in many situations that's true, but you could, for example, use something like server-side events or WebSockets. And in these situations, we often use GraphQL, for example, because it's a perfect fit, yeah? Because GraphQL defines subscriptions as first-class citizens. Yeah? In GraphQL, you can query data and you can subscribe to data. And whenever something changes and you have a subscription, you will directly get these changes pushed, right? And that's why I always say GraphQL is beautiful when you only work with mutations and subscriptions, right? So you mutate data and this will trigger a lot of subscriptions. And there is no concept of, caching or reloading needed. You really get data pushed end-to-end. And this is what we tend to call end-to-end reactive systems. And this out-of-the-box real-time capabilities are really great in many aspects or in many domains. And one last thing which this kind of architecture enables is that we can easily, not easily, but we have a way to strangle down monoliths, for example. Because, every system kind of has this legacy core or these legacy systems which we need to deal with them. And that's tough, right? And even tougher is to work with the data from those systems. And usually those systems, for example, store the user, right? And in this situation, this working with streams and working in a reactive way enables us to easily or more easily decompose these monoliths, right? So we could, for example, use change data capture. And what I mentioned already before is that change data capture is nothing else than each database kind of keeps an event source in its database. So we could easily check what changed over the time, and we could consume these events with tools like Decomposition or other change data capture tools and forward whenever a user was changed in the user table in our database to our event stream. And from there on, we can then consume them in newly created services, right? Newly fully independent services which are not affected by downtimes or by problems in the legacy services because we can push the data from our legacy into our new service. And that's, as mentioned, a very interesting concept when it comes to monolith decomposition. And we could also do this the other way around. But yeah, of course, in reality, it's much more complex than it's here shown on the slides. I mean, that's, I guess, true for most of the slides I showed you, but in the context of migration, of course. But when we do a lot of monolith decomposition projects these days, we usually always use change data capture. Not only, but it's really an important tool in our strategies to decompose monoliths. And that's kind of the last generation or the current generation, the third generation of microservices, which we tend to call fully reactive, right? So we have this advantage of being high resilient. We have horizontal scaling, we can have real-time integration, and we have even good integration with legacy systems. But we have a few minutes left, and I would talk a little bit about scaling, because there's even another generation of microservices. And if we talk about scaling, then we are all aware of those dimensions of scaling, right? We know there are these two dimensions. The one is vertical, the other one is horizontal. And usually we have a service and we can scale it up vertically, so we can put more CPU, we could put more memory, we could put more disk space on it. But actually that's not the way we want to go because it turns out to be very cost intensive on the cloud and things like this. So we usually want to go with horizontal scaling, so we want not to increase the power of one service, but we want to have multiple instances of the service running, right? I think that's kind of the classical knowledge when we talk about cloud-native architectures. And that's usually where everybody is aware of and where we usually stop. But it's interesting that we have a third dimension of scaling. And this third dimension of scaling is usually called sharding. And what does this mean now? We can shard our services, right? We don't only can horizontally scale our services, we can also shard them. So we could, for example, say, we put shards on those services, and those shards are basically defined by user groups, right? So we can say the first user group goes to this service, the second user group goes to this service, and the third user group goes to this service. And we can then combine those things, and we can change the user groups, maybe based on countries, but still we can horizontally scale. We can say, you know, in Norway we have a lot of users, so we need to spin up a second service. In Great Britain, we even have more users, so we need to spin up more and more services. And this concept of sharding is very important when you take reactive architectures a step further. Because ultimately what you have is you have a user event, right? So a user triggered a payment, and this user event gets stored into a stream. And now all kind of common streaming platforms like Apache Kafka, like Apache Pulsar, even if you use a Redis for kind of PubSub or streaming, then they work with the concept of shards. They usually tend to call it partitions. Redis, for example, even calls it shards, but Kafka and Pulsar and most of the others call them partitions. And basically, your event goes into a specific partition, and that's usually defined based on a user key or whatever you define for your partitioning. And that's basically sharding. So we take this event and move it into one partition, right? And from there on, we have then sharded services. We have, for example, 3 instances of our services which listen to different shards in our architecture. And we can say, you know, for this user group, it will always go into partition 1, and we will always have this service listening to the partition 1. And from there, we can forward it. We can say, okay, we make fraud detection. Or basically, we create an event that the payment is valid, and from there on, we consume it again in a sharded way via fraud detection. This fraud detection then again creates an event and says, "Hey, please, the payment is checked. Let's execute it." And the ledger is then again sharded. You know, the ledger is sharded in a way that only parts of the ledger work with parts of our user base. And then basically, we can take this folder and move it into a stream, which is ultimately the transaction stream where all transactions which were booked are stored. And the important part is now, if the fraud detection services, they usually need transaction information, right? And we can easily project this data back, of course, from this transaction topic into our fraud detection. And the important part is that we really just need to stay into our shard, because we can always ensure that in one shard there is a specific user, and the user will always be in the same shard. So we don't need to stream back all our kind of transactions. We just really need to stream back the transaction from the shard way in. And this, of course, makes the system much more scalable and much more performant, right? And tools we usually use here for this kind of streaming architectures, then Kafka Streams or Apache Think. And from there on, we can then basically move those events forwards to a data sync. And for example, Elasticsearch is a good data sync for transactions, right? And Elasticsearch again works internally with shard, doesn't really matter now, but they scale also with the concept of shards. But we can then, for example, go to this Elasticsearch and consume the transactions from our web banking from there. And this kind of makes this system super resilient, and also makes it kind of fantastic when it comes to throughput. Yeah, you can push massively data through this system. Yeah, it's not really possible to break the system. I worked for an Austrian financial institute, and we built an application sharded with 24 partitions based on Kafka. So we had 24 instances, right, sharded in a way that there could not be that much traffic, basically, that you really kind of break this architecture. And that's, of course, very powerful. It's also very complex, but when it comes to the scale and when it comes to the throughput, this is, I think, you cannot really find a way to get this more performant. And that's kind of the latest, I would say, architectural trend when it comes to microservices, which we tend to call stream-based, so sharded in a very stream-based approach. And this, of course, creates massive throughput. This allows us extreme scalability, right? And we are nearly at the end, so let's sum up here. I know this was a lot of tough stuff. I hope you kind of were able to follow, but I wanted to bring in as much as possible to give you this overview of the different kind of architectural patterns we see emerging on a microservice scale. And let's sum up here now. So
an important thing which I didn't mention, and I mentioned in the beginning that I work a lot with startups and scale-ups and stuff like this, and all of them have one thing in common. They started with a monolith, right? And I know it always depends, but I tell you, if you do something, start with a monolith, right? That's what I can probably say for sure. Start with a monolith, it's the best way to start, right? Because if those startups would have started with stream-based or reactive architectures, they would have invested all the time in these technical details, but didn't deliver business value. So first of all, very important, I guess you all know, start with a monolith. This monolith grows over time, right? Then we maybe need to split this monolith. And the way to split it is splitting it synchronously, as we have seen in the beginning. Don't do this. Just don't do it. It creates pain, it doesn't create any benefit. Actually, you always end up in a distributed monolith. Just really don't do this. If you need to kind of split it, think then of going with a monolith, right? So a well-defined monolith. And if at some point in time this doesn't work for you anymore because you need to have multiple processes, then maybe think of integrating or splitting up your system in an asynchronous way, right? And then at some point in time, you will automatically run into this problem of shared data. And then you need to twist, right? So you need to shift the dependency or the data flow actually. And you will ultimately always end up in kind of reactive systems because you want your data to be pushed to the downstreams and not pulled from the downstreams. So basically that's what reactivity is about, right? Moving from pull to push. And if this is still not enough, and if you still need more performance, more throughput, then you could think of the streaming architecture I showed you very shortly in the end. And this allows us massive throughput. So always start on the left-hand side and try to migrate from left to right? And there are fantastic reasons to go to the right-hand side. Don't get me wrong. Fantastic reasons like availability, resilience, scalability, throughput, all these things. But there are also very bad reasons to go to the right-hand side, right? And of course, as always in software architecture, we pay with complexity. So my advice, start on the left-hand side and always think twice how far to the right you have to go. That was it. This was about reactive architectures. I hope I made you rethink in reactive architectures. Hope this was useful. Thanks a lot. I think we're a little bit out of time, right? And, but yeah, if you have any questions, feel free to ask them now if we have time left, or yeah, reach out afterwards. I'm here for the rest of today. One more thing, I nearly forgot. We do a community training, so a free community training on reactive architectures, I think somewhere next week. So we will dive a little bit more into this concept which I showed you on state stores, projections, streaming and so on, but really more hands-on, so kind of coding this stuff. So maybe this could be a good fit to what I told you in this talk so far about reactive architectures. Any questions? Yeah? How much activities?
Yeah, how much traffic or things like that, before you see the actual needs.
Okay, yeah. Well, that's a tough question, right? When is the right time to split up a monolith, right? And I would say it's better late than too early. But of course, at some point in time, it creates a lot of pain, right? And usually you anyway feel it, right? If you have, usually in startups, you see they started with one team, and then at some point in time, there are 5 teams, and if still 5 teams still need to work all on the same monolithic code base, then it's usually time to split up, right? And then again, based on customer journey, it's very important. Don't take out entities, take out customer journeys, and take out those customer journeys which bring the most value and where you need scaling. For example, triggering a payment in a bank or in a fintech, right? And I would move them out, and I would try to keep them very independent in the beginning. Would really just make asynchronous integration there. And then when we need kind of more data integration between those separate services, then we need anyway to become reactive because we need to push data, right? And then there's the way to go there. And for example, payment is a good example because then you could even take this further and move it to streaming, because in payment you can have the demands for high scalability and high throughput. Yeah. Did this answer your question?
Okay, that's a tough question. When do you move to the right, basically, on this diagram I showed you in the end? And that's, a lot of companies die on these decisions. Honestly, they die because they don't get rid of the monolith, so they cannot produce business value in an acceptable time anymore. And others start too early. So they die because they do not produce business value anymore because they invest all the time in, decomposing monoliths and building, beautiful microservice architecture without any real business purpose. Yeah. Cool. I think we're done. Have a great conference. It was nice to be here. And yeah, stay safe.